chapter 2. Now, for the stress field, we will introduce the stress field. So whenever we study fluid mechanics, we should take into consideration different types of forces that can act on fluid particles. So you have the first type of forces is surface forces. For example, you can have pressure forces, you can have friction between the particles. All of these forces are contact forces, and we call them surface forces. And they are due to the contact between particles with a solid surface, or with particles one with each other. And a second type of forces that we can face is body forces, which are of type, for example, of gravity or electromagnetic forces, and they are experienced throughout the particle and at distance. Now, whenever we have a particle, we can define a certain stress field in different directions. Okay, so to do so, we can consider, for example, a certain area, and consider that for the surface forces will be divided into two components: one that is normal to the surface, and one that is tangential to the surface. And therefore, we can define two types of stresses. We have the shear stresses tau. So when you see this symbol, this is the symbol of shear stress, and sigma is the symbol of normal stress. So the normal stress is correlated to the normal force, and the normal stress can be given by the limit when delta A tends to 0. So if we consider a very small surface, and we consider a certain force acting on it, then the normal stress is the limit when delta A tends to 0 of del F over del A. Because you know that in general, it's like pressure. How you define pressure? Pressure force is force over area. In general, we might not have constant pressure over the whole area. This is why we define at each point what is the stress. So then the normal stress here will be defined as limit of del F over del A, while for the shear stress, we consider it's related to the tangential force in the plane of the area considered, and the shear is equal to a limit when the area of consideration tends to 0 of del F tangential over del A. Now, how we can completely define the stress field in 3 dimensions. So in case you are working in 3D, then you need to define a matrix of stresses as presented here. Okay, and we will go into detail over the different components of this matrix. So let us consider the following 3D figure. You have a certain cubic element, and you want to assess all forces acting on it. So for each face, you will consider both shear forces and normal forces. Now, to differentiate between the stresses and shear forces acting at different planes, okay, we will use a subscript notation, and we will define it together now. So first, in general, the first subscript will indicate the plane on which the stress is acting. To indicate the plane, you will just indicate the subscript of the normal to the plane. So for example, if you are working on this plane here, okay, then this plane is parallel to XZ plane, so its unit vector will be directed, its normal vector will be directed along y-axis. So the normal direction is y. For this reason, you can see here that all stresses and normal stresses and shear stresses subscript will start by y. So this vector, since it's perpendicular to the surface, it's a normal stress, so it's symbolized by sigma. Now the first subscript is y, sigma y, because it's the plane on which it's acting has a normal vector directed along y. Now for the second subscript will indicate the direction in which the stress acts. So here, since this normal stress is acting along y, so the second subscript will be y. So this stress is called sigma y. Now, let us move to the shear stress in this plane. You have two directions in the plane. So you have a shear stress along z, and you have a shear stress along x. Okay, how to name them? So the same, we will follow the same procedure. So it's a shear stress, so tau. Now, since we are working in plane xz, the normal vector is along y, so the first subscript will be y. Now, since this shear stress is acting parallel to x, so it's directed along x, then the second subscript will be x. And for this shear stress, the second shear stress in this plane, we will name it as follow. It's a shear stress because it's parallel to the plane, so it's tau. The first subscript is y because it's acting in a plane perpendicular to y direction. And the second subscript is z because it's acting parallel to z. We will follow the same way to name all remaining stresses. I will take another example. So if I consider now the following face, this face is parallel to plane YZ. So if I consider a shear for stress acting in this plane, then the first subscript, so first this shear vector tau is along a plane perpendicular to x, so the first subscript will be x. And the second subscript is the direction along which the stress is. For this one, it's y, because it's parallel to the y-axis. So this is tau xy, while the other shear component will have the same first subscript, because it's in the plane yz, so perpendicular to x, but the second subscript will be z, since it's parallel to z. So by doing so, we can define 9 stresses, okay, and we can put them in a matrix. You have tau xx, tau xy, tau xy, tau xz. So for example, these stresses all are applied on one common plane, which is perpendicular to what? Which is perpendicular to x direction. Okay, because for these three, the first subscript is x. So these are shear stresses acting on face YZ. Okay. While for the second line, you have tau yx, sigma yy, and tau yz. So these stresses are acting in a plane parallel to xz. And finally, you have for the third line, you have these stresses are acting on a plane parallel to yx. Now, how to know if a stress is positive or negative? You have a condition. First, for the normal stress, normal stress is always positive when it's causing tension, and it's negative when it is tending to cause compression. Now, concerning for the shear stress, okay, you consider it positive if both x and y, the corresponding x and y, are positive, or both are negative. What do we mean by this? So for example, here, if we consider the following shear stress, okay, tau xz. Tau xz is acting in a plane for which the normal is along negative x. So this is negative x direction. Okay, so to be considered as positive, it should be directed along negative z. This is why when they presented tau xz, they presented in the negative z direction. So here you have all arrows in this figure correspond to the positive convention. So the positive convention will consider that for I should have the same sign for both x and z. So when I consider, let's say, tau yz here, for this vector, okay, also you have z, you have it normal to this plane, to plane GX. So the normal to the plane is along Y, it's along negative Y. So to have tau YZ positive, it should be directed along negative Z. Okay, this is how you know if your shear, what is the way to consider positive shear and what is the way to consider negative shear. Any question on this? Okay. Now I will move to the introduction of the viscosity concept. The viscosity concept is very important in fluids because it will allow us to understand how fluids behave. If you consider the following fluid element and you apply on it a certain force, it will undergo a deformation. So the way to define a fluid is that the fluid will undergo continuous deformation when we apply on it a certain force, as opposed to a solid. If you consider a solid, the solid will just do a small deformation. However, the fluid will continuously deform. To understand this, if you look at the following figure, initially you have this fluid element, and you will apply on the top surface of this fluid a certain force. This force will cause a continuous motion of the fluid particles. So all fluid particles in contact with this plate will move in a continuous way. Okay. Therefore, we can define a certain displacement. So if I observe this fluid control volume for a certain time, delta t, it will move a certain, all particles at the top layer will move a certain distance, delta L. And this distance of motion will be defined function of velocity and time. So we can say that del L is del U by del T. But at the same time, we can define del L by another way because del L constitutes a deformation. So this is del L. It's the distance moved by a certain particle. Now, not all particles in the fluid will move the same distance because look, the particles in contact with the moving plate will move the largest distance, while the particles in contact with the fixed plate will remain in their position. Why? Because whenever we have viscosity, when it is a viscous flow, we have what is called the non-slip condition. What do we mean by the non-slip condition? We mean that if a particle is in contact with a certain surface, it will have the same velocity of the surface. So since this plate is fixed, then all particles in contact with this plate will have a velocity of 0. While particles in contact with the upper plate, which is moving at a certain velocity u, will have the same velocity of the moving plate. This will cause a gradual variation of the velocity within the fluid layers. Okay, so each particle, so for example, this particle will move to this position. Let's say this particle will move to this position. So the larger velocity will be at the top plate and the lowest one at the fixed plate. Therefore, we can geometrically relate the displacement delta L here to the change in angle of the line of particles we are observing. Because look, if you follow a certain line of particles, this line OP will have a new position after time delta t. It will be at position OP prime. Okay, so we can define a small variation in the angle of this line. This angle, we'll call it del alpha. It's a small deformation angle because we are considering a small time step del t. And then we can say that the distance del L can be computed as del alpha times the depth of the fluid del Y. This depth del Y. Why we can do this? Because from math, you know that if you have a very small angle, okay, if you have a very small angle, you can approximate the segment here by the length of the arc of circle. And the length of the arc of circle is the radius times the angle. So you can approximate the deformation del L by del Y times the deformation angle del alpha. From here, by replacing, if you replace del L by its expression here, okay, you can conclude that we can relate what is called the deformation rate. Okay, the deformation rate is related to the change of angle alpha with respect to time, to the variation of velocity with y. Because if I replace here del L by del y times del alpha, I will be able then to take del t to the other side. So if I take del t now to this side and del y to this side, I will get the following relation, which will relate the deformation rate to the gradient of velocity in the fluid with the thickness of the fluid y. So we know from mechanics of materials, okay, that the deformation rate can be related to the shear stress. Okay, so we can say that a fluid element, when subjected to a shear stress, will experience a certain rate of deformation, and we can experimentally investigate what will be the relation between the shear rate and the rate of deformation. Okay, so all of these results that are plotted here in the following slide are experimental results. So we know that the fluid will be affected by the deformation in the fluid will be affected by the velocity profile variation in the fluid. This is why what we did, we conducted experiments to try to relate the shear stress acting on the fluid particles to the gradient of velocity in the particle. And to do so, we did some experiments. We plotted the variation of the shear stress tau with the deformation rate. And this is what we deduced. If we observe the behavior of different fluids, we can come up with several categories of fluids. The main one that we will work with in this course is Newtonian fluids. Newtonian fluids are characterized by constant viscosity. What do we mean by viscosity? Viscosity is the ability of a fluid to resist variation in velocity within the fluid. To understand it more, I will do for you the analogy with Newton's law. In Newton's law, you have sum of forces equals to ma. In dynamics, you have seen that for the same sum of forces, larger the mass, lower will be the acceleration. This is why we say we define the mass as the ability of an object to resist motion, okay? To resist acceleration, if you want, specifically. So as the mass will resist acceleration for solids, in fluids, the viscosity will resist variation of velocity, because du by dy represents the gradient of velocity within the fluid. So if I fix the shear stress applied, larger is the viscosity, lower will be the gradient of velocity within the fluid. And this means that it will resist to variation of velocity between the particles. Now, if I have a Newtonian fluid, this parameter, which is called the viscosity, is constant. If not, if I have a non-Newtonian fluid, the viscosity can be variable, and we have different shapes that can be done for different fluids, and we will study these shapes in the following graphs. So to start with, for the Newtonian fluid, if I plot the shear stress function of the deformation rate, I will just obtain a straight line. Why I will obtain a straight line? Because mu represents the slope. Mu, which is the viscosity, represents the slope of the shear stress function of the deformation rate. Since we said that a Newtonian fluid mu is constant, so we expect that for a Newtonian fluid, if I draw the variation of shear stress with deformation rate, I will obtain a straight line of constant slope alpha. Okay, which is here alpha is equal to the viscosity of the fluid. Now, you have several types of fluids behavior. If it's non-Newtonian, you can then define a certain coefficient that you will call apparent viscosity, and the apparent viscosity will be related to a certain coefficient A and to a certain coefficient N through the following relation. So the apparent viscosity is K times absolute value of du over dy times n minus 1. And experimentally, we can determine parameters K and N. So to be able to understand the behavior of the fluid, and we should find what are K and N. To do so, we perform experiments. And from experiments, when we do a plot, we do curve fitting. So we can do a curve fitting technique to find what is K and N. Okay. Now, what we will do, we will see what is the different possible behaviors. So if we consider, we call some fluids are characterized by increased viscosity with deformation rate. So for example, if you look at the following curve, we said that the viscosity or apparent viscosity is the slope, represents the slope of the shear stress variation with deformation rate. So here, for dilatant fluids, if you follow the slope, it's increasing. So for these types of fluids, higher is the deformation rate, larger is the viscosity. For example, you can understand this. Some fluids, if you apply shear on them, if you mix them, they become thicker. This is the case of a dilated fluid. Okay, while if when I increase the deformation rate, the viscosity decreases. So here, for example, for pseudoplastic behavior, as I increase the viscosity, as I increase the shear, the deformation rate, what will happen is that the slope of variation of the shear stress is reduced. So here my viscosity, my apparent viscosity is being reduced with deformation rate. I will give you an example of this. Let's say if you paint a wall, okay? At the beginning, when you use the brush, the fluid seems viscous to you. But once you apply shear on the wall to paint the wall, it will become less viscous and it will spread on the wall. So in this case, higher is the shear stress involved, lower will be my viscosity. Another possible behavior is Bingham plastic. Okay, so in this case, for Bingham plastic, what will happen is that for a certain interval of shear stress, so if I increase shear stress, for example, from 0 to a certain value here, the fluid will act, it's not, the material I have will act as a solid, not as a fluid. But once I overcome this shear stress, when I overcome this limit, when I exceed it, then what will happen is that my fluid will start, my material will start to behave as a fluid. So in this case, you have a mixed behavior. For this interval of shear stress, it's acting as a solid, and after this shear stress, it's acting as a fluid. I will give you examples of this. If you consider the toothpaste, okay, the toothpaste, when you don't squeeze it, it's acting as a solid. It's not, it's rigid and it's not moving. Okay, while when you squeeze the toothpaste, it will start to deform and it will act as a fluid. So this is because when you squeeze it, you will apply a certain shear forces on it, and when you exceed the limit, the limit of transition from solid to fluid, it will start to deform continuously and act as a fluid. So here, in the following graph, they are drawing the apparent viscosity for the different types of fluids. So as we said, for the Newtonian fluid, we have constant viscosity. Okay, for the pseudoplastic fluid, the viscosity is decreasing with the deformation rate. While for the Dilatant fluid is increasing, the viscosity is increasing with the deformation rate. So understanding the concept of viscosity will allow us to define different types of fluids. Okay, so we can break fluid mechanics into several categories depending on their viscosity. So first, the first category is inviscid fluids. Inviscid fluids are characterized by zero viscosity. So they cannot resist. What do we mean by inviscid? When I don't have a viscosity, I cannot resist a change of a gradient of velocity within the fluid. So if you have an inviscid fluid, and you go back to the previous example where you have here a fixed plate, and here you are moving the particles. If it's inviscid, all particles will move at same velocity because this fluid is not able to resist velocity variation within the fluid. The second type is viscous. When we say viscous fluid, this means that we have a certain viscosity different than zero. And we will mainly work on this category. Okay. Now, viscous flows can be decomposed into laminar and turbulent flows. So now we will define what is the difference between laminar and turbulent flows. And also we can tackle, for both cases, for laminar and turbulent flows, we will consider internal and external flows. So we will define all of these types in the coming slides. And now for inviscid flows, we will talk about compressible and incompressible fluid flows. Now, let us start by classifying fluid motions. So as we said, first we will compare viscous versus inviscid flows. So when we say viscous, as we said, we have a viscosity different than zero, while for inviscid flows, we have mu equals to zero. So we can estimate whether or not viscous forces as opposed to pressure forces are negligible by simply computing the Reynolds number. So sometimes you have viscosity, okay, but this viscosity effect can be negligible compared to other forces. This is why in this case, even if we have viscosity, we can treat the flow as inviscid. So it depends if the viscosity is very small. So if the viscosity is very, very small, the behavior will be close to the inviscid fluid. And we can assess this by the Reynolds number. What is the Reynolds number? The Reynolds number is the ratio of inertia forces, which are related to motion of the fluid, to viscous forces. And it is a non-dimensional parameter. So you don't have dimensions for this parameter. You can check this. If you check units, the dimension of Reynolds number is 1. Okay. So, and physically it represents the ratio, the Reynolds number is the ratio of inertia forces, which are related to motion of the fluid. So inertia forces, this is why here you have the parameter V. So you have in the numerator is proportional to V, to rho, because you know that inertia forces are proportional to mass and to acceleration. Okay, so I have rho VL over mu, and mu is related to viscous forces. So if you do the ratio of inertia to viscous forces, you will end up with the Reynolds number. And for very high Reynolds numbers, okay, when you have very high Reynolds numbers, this means that the inertia forces are dominant over the viscous forces. Then the behavior of your fluid will be close to the inviscid behavior. While for small Reynolds number, where the viscous effects are important, then the behavior will be close to viscous fluids. So here, for example, we are studying, let's say, flow over over different surfaces. So here you have the flow over a sphere. So if it's an inviscid flow, what will happen is that you will not have particles sticking to the your sphere, because when it's viscous, as we said, whenever I have the fluid in contact with the surface, it is forced to have the same velocity of the surface. So if we have a viscous flow, what will happen is that in this region, your fluid particles will stick to the sphere, and you will have zero velocity at this level. And after this, you will have a certain separation point when particles will leave the sphere. And this will create a certain wake region behind the sphere. While for the case of an inviscid flow, this observation will not be there, because the fluid will not have to stick to the sphere, since it's not satisfying the non-slip boundary condition, because it's not a viscous flow. Okay, so even if it's contact with the surface, it will not experience this gradient of velocity, because it doesn't have a viscosity to resist velocity variation. So it will keep moving here, and you will not see a wake region behind the sphere. Another type of flows is flow over flat plates. So here, for example, if it's a viscous flow, what will happen is that because it's viscous, when in contact with the surface that is fixed, the particles in contact with the surface will be forced to have velocity of zero. So as you can see here, this will lead to the development of a certain boundary layer region, where you have progressive increase of velocity from zero to the velocity of the flow, because your flow was moving at you at a uniform velocity, let's say. Once it's in contact with the fixed surface, what will happen here is that the viscous forces will be dominant, because you are imposing a zero velocity here, and compared to u velocity, to a certain u velocity. So because of viscosity of your fluid, you will have resistance to transition of velocity. So you will have velocity gradients from zero to big U. And this is the profile of the velocity variation until a certain region, when the viscous effect will damp out, when you are far enough from the surface, then you can reach a certain region where you can call it inviscid flow, because in this region you don't have any more effect of viscosity, since you don't have gradient of velocity here. So if you want, in this region, the inertia forces will be dominant over the viscous forces, and then you will end up with in this region you will have a uniform flow and no viscous effects. While close to the surface, due to imposed gradient of velocity, you have the viscous effect will lead to a transition region from zero to u, and this is called the viscous boundary layer. So due to viscous effects, you will have the formation of a boundary layer, and after this, far from the wall, you will have a certain inviscid flow region where you have no gradient in velocity. Now, as we said, we have different types for classification of fluid motions. Second criterion that can be used is to differentiate between laminar and turbulent flows. Okay, by definition, a laminar flow is one in which the fluid particles are moving in smooth layers. So as you can see in the following figure, let's say, if you observe the motion of particles, it is very smooth. You don't see mixture of particles. You don't see random motion of particles. So it's a very smooth variation. So as you can see here, if you put particles and follow, or you put smoke, you can follow the behavior of fluid. So if you do an observation here for your streamlines will be straight lines, and they are very organized. Okay, so this is a laminar flow. While for the turbulent flow, if you look at the turbulent flow, you will see that particles will rapidly mix, and they will move in random three-dimensional directions. So you will have a lot of velocity fluctuations, and therefore, if you are tracking these particles, or if you are injecting smoke within the flow, you will see this behavior, this random behavior. So it's not organized. It's you have mixing of particles, etc. So this is a turbulent flow. Okay. Now we will have some criteria to define how a fluid can be characterized as laminar or as turbulent. So when we talk about laminar flow in a one-dimensional flow, the shear stress will be related to the velocity gradient by the simple relations that we have seen together before. So this is applicable for the the viscosity relation with shear and deformation rate is valid in this form for laminar flow. Now, in case of turbulent flow, in which the mean velocity field is one-dimensional, you will not have such simple relations that is valid. In this case, it is much more complex to study the flow, and in general, we we do a lot of experiments to come up with certain empirical, semi-empirical theories that can be applied to turbulent flows. Turbulent flows are very challenging, and they require advanced tools to solve them. So, for example, in general, we use computational fluid dynamics, FD. So you will use a certain software that will code all equations. We will see them together after the Navier-Stokes equations. It will implement them in algebraic equations, and it will use certain schemes to solve for turbulent flows. But it is a complex thing beyond the scope of the course. But in this course, we will introduce you to some techniques that can be used to treat such flows. So as you can see here, this is a small comparison. If I draw, let's say, a streamline, okay? If I follow a particle in a laminar flow and a turbulent flow, you can see the difference in behavior. As we said, in laminar, it's very organized, while in turbulent, it's a random and fluctuating motion. And the main criterion that will be used to differentiate laminar and turbulent flow is the Reynolds number. Because we will see that for small Reynolds number, you will have a laminar flow, and for a large Reynolds number, we will have turbulent flows. Okay, so we will see that for which values of Reynolds we can consider a flow as turbulent. We'll see in the coming slides. Now, another possibility to describe and classify fluid motion is to consider the difference between compressible and incompressible flows. So flows in which the variations in density are negligible are termed incompressible. And in general, the majority of liquids are incompressible. So if you deal with liquid, water, if you consider water, if you consider oil, liquids are incompressible. Now, if we talk about gases, for gases, we can categorize both. We can find compressible and incompressible gases. In general, a gas is compressible, as you know, but the behavior of a gas can be approximated as incompressible in certain conditions. Okay. So when the density variation within a flow are not negligible, the flow is called compressible. But if we have variation but very small, we can model it as incompressible. Now, how to define? We will define a certain parameter that will allow us to judge the compressibility. The parameter is the bulk compressibility modulus. This modulus is defined as follows. So it's equal to dp over d rho over rho. Okay. Now, how to understand this definition? If you look at the factors involved here, it means how much I should vary the pressure, okay, to induce a certain change in density. So let us think together. If a fluid is incompressible, this means that I should put on it a very large pressure variation to induce a density change. So if a flow is incompressible, the bulk modulus should be very large. While if a flow is compressible, then EV should be low. Because when I say compressible, this means that I don't need a lot of effort to change the volume or to change the density. Okay, so small EV will correspond to compressible flows, while large EV will correspond to incompressible flows. Now, in general, gas flows with negligible heat transfer and with Mach number smaller than 0.3 can be treated as incompressible. So gases are compressible, but if they satisfy the following conditions, negligible heat transfer, and the Mach number, and we'll see what is the Mach number, and the Mach number smaller than 0.3, I can treat them as incompressible. Now, what is the Mach number? The Mach number is defined as follows. So Mach number is V over C, where V represents the speed of sound in a certain ideal gas. Okay, so you have C is the speed of sound in an ideal gas, and V is the velocity of sound in the medium you are considering. So let's say you are considering air, for example. Okay, and you want to know if in the conditions of air you have, if you can treat it as incompressible or not. So you should make sure that its Mach number is smaller than 0.3. To do so, you can perform experiments in the conditions you have to calculate what is the speed of sound in this medium. And then you will compare it to C, which is the speed of sound in an ideal gas, and it's given by radical KRT. Okay? Now, in case this ratio is smaller than 0.3, and I have a negligible heat transfer in the medium I am considering, then I will treat it as incompressible. If not, I will treat it as compressible.
دكتور
Yes.
هن بس in general بيكونوا كلهم incompressible مش هيك؟ ما بيجي يعني case compressible.
In general مظبوط، نحن حنشتغل على incompressible flows in general. Okay. But just this is for you to know the difference between them. Any other question on this? Okay.
دكتور بس عندي question بخصوص الفيديو.
Yes, أكيد. If you have a question for previous slides, tell me.
اوكي اخر فيديو بس هو عن شو الدايمنشن وهيدا عن شو يعني؟
بس can you if it's possible to raise your voice and I'm not hearing you well.
اخر فيديو نزلتيه عن dimensions. انا ما لحقت احضر كله
عن units and dimensions.
هيدا chapter 1 هو
هيدا chapter 1 مزبوط. وهلا من بعد ما خلصنا chapter 2 today I will post for you انا حطيت لكم على e-learning problems عن chapter 1 و 2. بالريكوردينجز حطيت لكم عن problem 1 solution لانه كنا بعد ما خلصنا chapter. Now as we are done with the chapter ححط لكم problems على viscosity.
Okay دكتور ميرسي.
And we will practice together now with these problems.
دكتور بعد طلب عندك شيء مثلا مثل ورقة بس للفورمولاز انت عملتيها او هيك ملخص نزلنا اياها؟
ايه اكيد
ملي معروف.
اوكي
ميرسي.
Okay, so let us start to do problems. For the first problem, okay, we already did it بالexamples. It's very similar. وحتى بالproblems اللي حطيت لكم اياهم على recordings, it's the same one. So if you want, try to practice with it, but it's the same concept. This is why I will move now to this problem. The velocity distribution for laminar flow between parallel plates is given by the following formula. U over U max is equal to 1 minus 2y over h squared, where h is the distance separating the plates and the origin is placed midway between the plates. Consider a flow of water at 15 degrees with U maximum equal to 0.1 meter per second and h equal to 0.1 millimeter. Calculate the shear stress on the upper plate and give its direction. Okay, so how should we think here? First, let us draw a small figure of the problem. So we have a laminar flow between two parallel plates. And as you can see, this flow is of parabolic shape. Okay, we have the distance between the two plates is equal to h. And as the profile is indicating, the maximum velocity is taking place at y equals to 0. So we can deduce this flow. This flow is between two fixed plates, okay? Because what is happening is that this is the center line. And I have for y equals to 0, I have u maximum, because if I replace in this equation, for y equal to 0, I get u over u max. So for y equals 0, u over u max is equal to 1. So I deduce that at the center of between the two plates, I have a maximum velocity equals to u max. Okay, and now for the extremities, since I'm considering this is my origin and this is y-axis, so I will have that the upper plate coordinate is plus h over 2. And the lower plate coordinate is minus h over 2. So now, if I want to calculate for this problem, what is the shear stress on the upper plate, I should apply which formula? Which formula give me the shear stress?
Tau yx
times du over dy.
Yes, very good. Tau is equal to mu times du over dy. Okay. Now let us make sure together here that if you replace y by h over 2 or minus h over 2, what do you get? If you replace here y by h over 2, okay, you will get 2h over 2h, which is 1. Okay. And if you replace by minus h over 2, you will get minus 1. So 1 and minus 1 square both will give you 1. 1 minus 1 is 0. This means that at the top and bottom plates, you will have a velocity of 0. And this is expected due to the non-slip condition. So this will be your velocity profile for the flow along this duct, or between these two plates, if you want. And now they asked for the shear stress on the upper plate. Since they want the shear stress on the upper plate, then we should calculate du by dy at y equals to plus h over 2. Okay. So all I have to do is first to derive this relation. Okay, I will derive u with respect to y, and then I will apply a du by dy at h over 2. Let us do it. So the function u can be written as u equals to u max times 1 minus, if I do here the development, it's 4 y square over h square. So 4 y square over h square. Let us derive this function to go. So du by dy will give us, I write it here. Du by dy is equal to, first I have a constant q max that is multiplying my my function, so it will be included in the derivative. So it's u max times now the derivative of minus 4y square over h square is minus 8y over h square. So it's times minus 8y over h square. Okay, and now I will replace to be able to know what is du by dy at the point of interest, which is at plus h over 2. All I have is to replace. Okay, so now if I replace here in this equation for plus h over 2, I will get the following. I will get 8 over 2 is 4. Okay, so I will get minus 4 u max over h, because h over h square will simplify, so I will just have minus 4u max over h. Look, if it's not clear for you here, I can write on a whiteboard. Is it clear for you to write over the problem, or you prefer to write on a whiteboard?
هلا واضحين دكتور.
Okay. So this is du by dy at the upper plate. Okay. Now I can say that the shear stress at the upper plate is minus 4u max over h times mu. Okay. Now I have the value of u max and I have the value of h. I can replace. But how can I get the value of mu? You're saying, what should I do? How to get mu?
هي viscosity تبع الووتر.
Very good. بس يعطوكم مثلا قالوا لنا انه it's water وقالوا لنا temperature, then you will have to go to a table بتكون موجودة بآخر البوك بالappendix. Okay, you go to the table which will give you the variation of viscosity with temperature, and you will select the viscosity of water at 15 degrees, and then by just replacing numerically you will get the top. Now let us do together some analysis. We got a negative shear. Okay, what does this mean? Let us go back to the definition of positive shear. Now I am looking at on which surface I am considering shear on this surface, على upper surface. اتفقنا؟ هيدا upper surface إذا بعمل النورمال تبعها, the normal تبعها is towards the fluid. So the normal direction تبعها is downward. يعني هي النورمال is negative y. فنحن اتفقنا انه الشير تيكون positive وقتها سمي الشير هون حيكون شو اسمه؟ الشير فورس هون حيكون اسمها تاو y اول شيء لانه it's acting along a plane perpendicular to y. يعني اول subscript حيكون y. subscript لانه انا عندي هون هيدي الدايركشن حسميها x. بما انه هيدا التاو تبعي هون is along x direction, فالشير ستريس on the plate حيكون اسمه تاو y x. اوكي, فنحن قلنا تيكون شير بوزيتيف بده يكون الواي تبعه والاكس تبعه اثنيناتهم بوزيتيف او اثنيناتهم نيجاتيف. بما انه الواي تبع هالشير نيجاتيف لانه النورمال فيكتور لتحت، اوكي، فاذا اذا بيطلع لي بوزيتيف شير يعني الاكس تبعه كمان بدها تكون نيجاتيف، بينما اذا طلع لي نيجاتيف شير يعني الاكس تبعه بدها تكون بوزيتيف. بما انه طلع لي نيجاتيف ريزلت للشير هون، كيف حيكون التاو هون؟ حيكون عنده بوزيتيف اكس لانه اوريدي عنده نيجاتيف واي. فاذا here since I got a negative along positive x and not، هيدا الشيء ليش منطقي؟ لانه
دكتور راح الصوت.
الفلويد بس يمشي بين البليت حيجي
مش عم نسمعك دكتور.
اذا بناخذ السيرفيس يلي تحت، اوكي، هلا بس بدنا نعمل اناليسيز لهيدي السيرفيس. النورمال فيكتور للسيرفيس حيكون upward، هو الفيكتور directed towards the fluid zone، اوكي. فاذا هون الواي تبعه بوزيتيف، فليت us check شو حيكون التاو واي اكس على هالسيرفيس، ونحن we expect كيف لازم يكون برايكم؟ اذا بجيب التاو لازم
دكتور
يكون
بعدك
to the
عندي
right او
شير
to the
سكرين.
left. Can you please repeat؟
عامل شير سكرين لانه مش مبين شيء.
اوكي. بينت شيء هلا؟
Yes, بيان.
Okay. So what we will have here now, if we consider minus h over 2، إذا بتحطوا مطرح y minus h over 2 هيطلع لكم نفس الريزلت بس بدل minus حتصير plus، اوكي؟ يعني الشير على اللور بليت حيكون positive. بما انه حيكون positive حارجع اطلع على الكونفنشن، فيكون الشير positive لازم الواي تبعه يكون positive والاكس تبعه يكون positive. فاوريدي الواي از positive، اوكي، ساعتها بما انه طلع لي شير positive then مفروض التاو على اللور بليت يكون كمان in the positive direction. وهيدا كمان شيء منطقي لانه الفلو هو وماشي حيجر التو بليتس to the right. بس وقت عملت اناليسيس على الابر بليت طلع لي نيجاتيف شير، وقت عملت اناليسيس على اللور بليت طلع لي بوزيتيف شير. How can I explain this? I can explain this من الكونفنشن، لانه نحن شفنا انه a shear is considered positive اذا both الواي والاكس تبعه are positive or اثنيناتهم نيجاتيف، اوكي. بس اذا وحده بوزيتيف وحده نيجاتيف بيكون الشير نيجاتيف in this case. فعطول بدي اطلع على الدايركشن اوف فيكتور نورمال تو ذا سيرفيس، وبدي اطلع على الساين اوف شير تعرف اذا الشير تبعي حيكون to the right or to the left. اوكي. Any question on this؟
دكتور انا بس عندي question بالاول بالدي يو اوفر دي واي، اذا فيك بس تعديل هي اعملي معك كيف طلعناها.
Guys ما عم بسمع ابدا. You know what, next time حنستعمل zoom is much better. اوكي.
عم بسألك بس اذا فيك تعديل
اذا
دي يو اوفر
بدك
دي واي.
ابعت لي your questions by WhatsApp لانه I'm not able to hear you.
اوكي دكتور.
Okay. طيب. Now, they asked us also to sketch the variation of shear stress across the channel. إذا بدي أرسم ال variation of shear stress، أوكي، هأطلع بالإيكويشن تبعي. الإيكويشن تبعي mu is constant، وعندي del u by del y هي function أنا جبتها أنا وياكم، هي function of هي linear function of y. So as you can see, shear stress will be varying in a linear way with y. بيكون positive على lower plate ونيجاتيف على الupper plate. يعني إذا بدي أرسمه حيكون بهالطريقة. إذا بدي أرسم الفاريشن تبعه، أوكي، وعندي بيمرق بالزيرو بالنص، لأنه بالنص عندي ماكسيمم. شو بيصير على الماكسيمم فيلوسيتي؟ على الماكسيمم فيلوسيتي del u by del y بتصير زيرو. فإذا عندي symmetrical variation of the shear stress about 0.0. على lower side بيكون positive shear، على upper side بيكون negative shear. اوكي. Let us move to another problem. As I told you guys, إذا في حيلا سؤال بعتوا لي إياه واتساب، لأنه I'm not hearing you well على Microsoft Teams. I will try next time to go back to Zoom لأنه بزوم it was better. Another problem. A block of mass big M slides on a thin film of oil. The film thickness is small h and the area of the block is big A. When released, the mass M exerts tension on the cord, causing the block to accelerate. Neglect friction in the pulley and air resistance. Develop an algebraic expression for the viscous force that acts on the block when it moves at a speed big V. Derive a differential equation for the block speed as a function of time and obtain an expression for the block speed as a function of time. The mass big M is 5 kg, small m is 1 kg, the area A is 25 centimeters square, and h is 0.5 millimeter. If it takes 1 second for the speed to reach 1 meter per second, find the oil viscosity. And finally, plot the curve for V function of time. هنعمل أنا وياكم analysis للproblem. I want you to try to do it on your own, and we will continue to correcting it completely next time. What do we have here? شو عنا هون؟ First, عنا combination بهذا الproblem of dynamics and fluids. يعني we will use both dynamics and fluids to be able to solve. Okay? خلينا نبلش بالداينامكس. نحن بنعرف من الداينامكس إنه when I have a cord and cable system وقتها بيكون frictionless pulley and massless pulley, we have that the tension is conserved over the cable. Okay? يعني التنشن إذا باخد the free body diagram to block M, what are the forces acting on it? I have first the tension in the cable T. عطول بالداينامكس أول شيء كنتوا تعملوه كنتوا ترسموا the free body diagram. So I have the tension, I have the weight, I have the normal reaction, and I have the friction due to what? Due to oil film. هيدي الفريكشن due to oil film is due to viscous effect. يعني the viscosity of oil حتخلق على البلوك friction forces اللي هي shear stress إذا بتكون جاية من shear stress. So هيدي الفريكشن that will act on the block is equal to the shear stress tau times the area of contact. Okay? This is the shear stress جاية من الأويل. Okay? والarea is given. A is 25 centimeters square. يعني القصة هلا انه جيب what is the shear stress. بما انه I am dealing with contact between a solid surface and a fluid, الشير مثل ما شفنا انا وياكم هو ميو times del u by del y. اوكي هلا هون شو هي الواي دايركشن؟ هي الدبس اوف او thickness of the fluid. يعني انا شو عندي هون؟ هيدي حاعمل لها زوم شوي، حاعمل لها سكتش هون. I have an oil film. اوكي هيدا الاويل فيلم عنده contact مع a lower surface that is fixed، عنده contact مع an upper surface that is moving. يعني عندي fluid between two plates, one fixed one moving. Due to this effect شو حيصير؟ حيصير في gradient of velocity within the fluid from 0 على fixed plate to big V على الكونتاكت مع البلوك. يعني الفلويد تبعي حيكون البارتيكلز يلي ان كونتاكت مع اللور سيرفيس الفيلوسيتي تبعهم 0، والبارتيكلز يلي ان كونتاكت مع الابر سيرفيس الفيلوسيتي تبعهم بيج في. اوكي هلا ان جنرال بس ما يقولوا لكم ولا انفورميشن، بس ما يعطوكم any information بالبروبلم ويكون عندي small thickness، فينا نعتبر we can assume a linear profile. يعني بنعتبر انه ال velocity variation بهيدا ال thickness of oil is in the linear form. اوكي ونحن سوا حنثبت بعدين وقت نشتغل على ال equations، حنثبت انا وياكم انه بس يكون عندي هيدا ال problem of one plate fixed one moving the velocity profile is linear. اوكي فاذا هون بما انه it's a linear velocity profile I can replace del u by del y اللي هو slope of this line. اوكي del u by del y can be replaced by delta u over delta y. What is delta u? delta u هي v minus 0. okay so I will replace delta u by big V minus 0 يعني big V. اوكي ودلتا y هي depth of oil اللي هي h. so I can replace del u by del y ب big V over h. يعني صار عندي expression of shear stress. shear stress is mu times big V over h. اوكي فلحديت هلا لقيت الشير function of velocity. بقى اكتب نيوتن لو للبوكس. بدي اكتب نيوتن لو للبوكس حيكون عندي several unknowns. عندي التنشن، acceleration of the block. okay so I need then to write another equation. ثاني equation حاستعملها هي الايكويشن للماس m. and what is common between big M and small m انه عندهم نفس الاكسلريشن. لانه انتم بتعرفوا من الداينامكس اذا عندي هذا السيستم اوف بولي، عندي one pulley with one cord. اوكي اذا باخذ coordinate system so this is the coordinate of big block حسميها S of big M. حاخذ coordinate للسمول block S of small m. بما انه it's a cord total length تبعها constant so شو فيني اكتب؟ فيني اكتب انه big SM plus small sm is equal to a constant. and now if I derive this relation بيطلع لي انه ال velocity of m is equal to minus the velocity of small m. If I derive a second time لأنه هيدي position. If you derive position with respect to time بيطلع لكم relation بين ال velocities. If you derive the velocity relation بيطلع لكم relation between accelerations. So if you derive two times بيطلع لكم إنه إنه acceleration of big M is equal to minus acceleration of small m. هلا ليش طلع لي minus؟ لأنه أنا آخذة هيدي الدايركشن as positive. بس أنتوا إذا بتاخذوا هيدي as positive، يعني بتعتبروا لأنه بتعرفوا إنه البلوك حيمشي هيك، فيكم تاخذوا هيد direction as positive، ساعتها بتصير ال A big M equals to A small m. يعني عندي common acceleration بين big M و small m, and if I use this information I can solve the problem. But please, I want you to try to do it on your own, and we will do the detailed solution together next time. Any question before we close? Okay, bye.
باي دكتور.